MTech from IIT Ropar, and he is working on hardware security, mainly on how to maintain the security of last level cache without compromising on the performance. So this is his main focus of his research. So thank you, Prathamesh, for agreeing for this talk, and over to you. There are, I think, 15, 20 students are there in this course, and they know all the basics required for understanding Hawkeye and Mockingjay. And Guru is also here; he will coordinate. And it's over to you now. So I'll not be here because I have another exam, so I'll leave now.
Sure. Okay. Thanks. Thanks, Dr. Shishindu. Uh, just a minute. Uh, just let me know if my screen is visible.
Yes, sir, it is visible.
Right. Uh, okay. So, good evening to one and all. My name is Prathamesh Nitin Tanksale, and I'm a PhD student here at IIT Ropar under the supervision of Dr. Shishendu and Dr. Kalyan. So, I think the composition of today's class is as instructed by Guru and Dr. Shishendu, mostly MTechs, PhDs, and BTech, right? So what we will do is we will try to stick to the basics and try to slightly build on topics of cache replacement, right? So just a quick input from your side. So what is the latest cache replacement policy which you guys are aware of? Any of the students can just ping me. uh, is someone putting it on? Right. My voice is audible, right?
Yes, sir, you are audible.
Fine.
Yes, Prathamesh, you are audible. So
Okay.
I'm requesting audience, please discuss with. Don't be just listen. Don't just listen it. So this is a important lecture, and based on this lecture, you have to the remaining lectures depend on these two concepts, Mockingjay and Hawkeye. So I'm listening it. I'll also observe that how are you responding or not. Okay, so please
Okay.
respond. If he is asking any question, try to answer, or at least if you don't want to speak, then type it in the chat box. That will also help. Okay, Prathamesh, please continue.
Yeah. Sure. Thanks. Okay. Uh, so I think we will start with the basics anyway. So let's try to build on it. So yes, we will start with some basics. So this is how we have planned for today's talk. So we will quickly discuss the background. We will also look at the motivation and insights. Then we'll look into the state of the art Hawkeye and Mockingjay results and the experimental setup and what are the key takeaways and future scope. Right. So let's start with background and let's try to keep this class as interactive as possible so that you might also get the most benefit out of it. So looking at the basic memory hierarchy, right? This is the memory hierarchy which we all have been growing up learning. So we have CPU registers, we have CPU caches, level 1, level 2, level 3, then we have main memory, and then we have storage, right? Now you can see these two arrows, which signifies that as we go down the hierarchy, the capacity kind of increases, right? But the latency also kinds of increases. So if we want good latency, we want to stick to the on chip part. So this is the on chip part, which consists of CPU registers, then we have CPU caches. So this is primarily the area of focus, right? Now, what's their inside? So typically we look into, CPU from outside looks something like this, but internally it's something like this, right? So if you look at a more micro analytical picture of, modern CPUs, what you will find is a hierarchy of caches and core, right? So if you look at the L1 cache and L2 cache, but if you look at the third L3 cache, right, which is the last level cache, this cache consists of typically in few MBs, and generally it occupies nearly 40% of on-chip area. So this is a very crucial and important component onto which lot of research has gone, right? So we'll look at the performance implication of those research, mainly from the performance of replacement policy point of view. Now, one may ask a very crucial question here, that why this last level cache is so important, right? So as we have this hierarchy of caches, so we may ask this question, that why the last level cache is particularly very important. So you might have gone through this least recently used replacement policy, right? So can anyone you quickly just give me a glimpse of what exactly is an LRU replacement policy? Maybe you can type on chat or something like that. The least recently used replacement policy.
So you have a bunch of blocks in the cache. You essentially have a queue. You push into one end. That's the most recently used position. And whenever you want to evict, you pop from the other end. That's the least recently used.
Yeah, thanks. Yeah, so that's the typical least recently used replacement policy, right? Now you may wonder that at level 1 and level 2 cache, this recently used replacement policy kind give you wonders, but why not at last level cache, right? So if you observe it carefully, you will see that most of the accesses are kind of filtered by this upper level L1 and L2 caches, right? Now at LLC, the application patterns are too variable or too complex, for the LRU to catch, and so the hit rate kind of drops. Now you may ask the question, what are these complex access patterns, right? Now typically a cache access pattern, can be classified into 3 or 4 types. So let's look into each of it in a little bit of detail. So this is a recency friendly access pattern, right? So in this pattern, you can see the blocks A1, A2 to AK-1 are accessed, and then again it is accessed in the backward manner, which is AK-1, and this kind of happens in a circular fashion, right? So do you think LRU will be able to capture such kind of pattern? And when I mean capture such kind of patterns, will LRU be able to give good amount of hit rate in this pattern? Any inputs from your side?
Well, yeah, that is why it's called recency friendly. It's friendly to LRU actually,
Right.
replacement.
Right, right. Thank you. Yeah. So that's why it's trying to enhance or trying to encapsulate this recency friendly activities, right? Now there is another pattern which is the thrashing access pattern, right? So when we look at this thrashing access pattern, this kind of access pattern is also very common, but here the K is greater than the cache size. So not the entire working set will be able to capture, right? So the replacement policy will not be able to capture the entire working set. There is another pattern which is streaming access pattern, where no matter which is the replacement policy, they will not be able to harness any recency benefits out of it, right? But here comes the fourth access pattern, which is the mixed access pattern. Now this is very crucial. Now if you look at the other three patterns, you will see a massive green flag here. Why? Because any recency friendly application with a bit of modification here or there can be able to adjust to these patterns. But what makes the fourth pattern really important is it has a bit of all the three. So you need an intelligent replacement policy to capture such complex access patterns and give you good enough cache hit rates. Now, modern workloads, as we see the workloads which we use in our modern systems, kind of are going towards this mixed access patterns, where the patterns are very difficult and the replacement policies which are proposed for just recency friendly, which give very low metadata, will not be able to capture it. So this is the area of interest for us. Now let's go into the motivation and insights. So this is a high level tree diagram for the replacement policy research, which has gone into this field for roughly past 20 to 25 years, which is past 2 decades, right? So a cache replacement policy can loosely be classified into two parts, which is coarse grain and fine grain, and then further it can be sub-classified. But now what is of our area of interest is to begin with the recency based policy known as SRRIP. Now, I presume that you have a basic idea of SRRIP, but we will slightly build on it. Now, any replacement policy has three sub policies within itself. So we have an insertion policy, a promotion policy, and an eviction policy, right? Now, can any one of you kindly, give an overview, or are you familiar with these terms, the insertion policy, promotion policy, and eviction policy?
Yes, I did them in class.
Sure, thank you. Yeah. So now when we try to break a replacement policy into three sub policy problem, right? So this SRRIP replacement policy, what it does is it gives a 2-bit state for each and every block, and all the bits represent the insertion, promotion, and eviction vectors. Now let's see an empty last level cache, which is a set associative cache. Let's say block A is accessing, right? Now it's an insertion and the cache is initially empty. So it will give an RRPV value of 2, right? Similarly B, similarly D and E. Now the cache is full. Now let's say again A is coming, right? So it will be a hit. Now because it's a hit, the promotion value will be 0. So the RRPV bits will be changed. So similarly, when C will access, it will be a miss in the cache. The replacement policy will be kicked. Now the RRIP replacement policy requires eviction bit to be 2 power n minus 1, which is 3 in our case. But as you see now no bit is having RRPV equal to 3, right? No block is having that. So what it will do, it will increment the RRPV of all the blocks by 1. So this 2 will now become 3. And now they will choose one of the eviction candidate, right? So maybe you guys are familiar with this, but this is really the bedrock or the foundation of Hawkeye and Mockingjay, or for that matter, any state of the art advanced replacement policies, right? So this is how bits are updated in the block. Now, if you look at the replacement policy research tree, there are many replacement policy on this side, and for our area of interest is the classification based replacement policy, where we have this Hawkeye and Mockingjay. Now these two replacement policy are really the state of the art replacement policies and has appeared very recently. So Mockingjay appeared in 2022 HPCA. So these all appeared in good forums. Now, before going into this, there is a very important crucial concept which is known as Bellidy's optimality, which is a theoretical concept which appeared, way back, which is like half a century ago, 50 years ago. So, does any one of you have any brief idea about this Bellidy's optimality?
Yeah, Beladi's replacement policy dictates that we want to probably evict the the block which is going to be accessed farthest in the future. So that is the idea.
Right, right. And why it's not been able to be implemented is because it's a
Because
theoretical.
we cannot predict, we cannot break the future, unfortunately.
Sure, sure. Yeah, thanks. So that's the that's the theoretical oracle which we are looking at. So that's the best which we can get, right? Now, in order to look at Bellidy's optimality, if we let's say if you look at this particular access pattern and this is the last level cache. So let's say these particular blocks are empty, so we fill in the cache. Now A, B, D, and E are filled, right? Now, when C will appear, there is no space in the cache. So what will happen is the Bellidy's optimality, as rightly pointed out by one of your colleague, will look at the farthest block which will be reused in the future, right? So in this working set example, can anyone of me let me know which will be the eviction candidate chosen here by the Bellidy? If the cache is currently having A, B, D, and E, and currently we are at C, now we have to insert C and evict one of the A, B, D, E. So which will be evicted?
D.
D, right?
Yeah.
Yeah, thanks. Yeah. So D is evicted because it will be used farthest into the future, right? So it will be chosen as the victim. Now, why we came to this particular example? Now, this is very important. Why we came to this particular example? Because this is the theoretical maximum which we can achieve. Now, any smart replacement policy which kind of tries to bridge that gap or go closer to Melody's optimality, should somehow find a way to mimic this activity, right? So this should be done in real time without looking at future. Now, is there a way to do so, right? That's the question which we are really trying to answer. Now let's jump straight into the heart of today's discussion, which is the Hawkeye and Mockingjay replacement policy, right? Now you might be familiar with these two comic characters. On the left side we have Hawkeye from Avengers and this Mockingjay from Hunger Games, right? So can you take a wild guess of why the researchers from this replacement policy came up with those names? Any wild guess from your side? Hawkeye and Mockingjay?
Uh, Hawkeye does something related to accuracy, right? Picks a target to evict somehow accurately, and I'm guessing Mockingjay is a hybrid of something.
Uh, yeah, close enough. Close enough. Hawkeye tries to pinpoint a target. Yeah, that's correct. That's one way to look at it. But anything other than anything more closely associated with Hawkeye or Mockingjay? Any other guess? Okay. Yeah. So here Hawkeye, so here the picture is quite misleading from my end, so sorry for that. But actually it was kind of proposed as hawks can see 8 times farther than humans, right? Now in Melody's optimal, so this is not the Hawkeye, so this was a trick thing by my side. So hawks are actually hawk bird, right? So that is able to see much more farther. And if you are trying to mimic the Melody's optimal replacement policy, you need to look far into the future, right? So that's why they came up with name Hawkeye. And for Mockingjay, it's a fictional bird in Hunger Games trilogy, which remarkably memorizes and mimics human melodies. So this work actually tried to mimic the Melody's optimality. That's why they came up with this name Mockingjay. Some of it sounds too far-fetched, but that's how they came up with it. Okay, so let's jump into it. So the Hawkeye paper actually appeared, in ISCA 2016. So ISCA is one of the top tier conferences in computer architecture field where, top class research activity happens. So the official name of the paper was Back to Future, leveraging Melody's algorithm for improved cache replacement, right? Now let's look at Hawkeye at a very high level, right? So what Hawkeye tries to do? So what Hawkeye tries to do is to create cache replacement problem as a binary classification problem, right? So what do we mean by a binary classification problem? The goal is to determine whether the incoming line is a cache friendly line or a cache averse line, right? So that's the problem. Now, once we are able to classify this cache friendly or cache averse, the cache friendly line will obviously insert it with a high priority in the cache, while the cache averse line will be marked as a eviction candidate, right? So basically very straightforward till this point of view. Now, this is the crucial concept, right? Now, if somehow we can look you into the future, right? How far into the future we need to look, right? Now Hawkeye came up with this particular aspect, which is if you look at this particular plot, that's very interesting because the title says to recreate Melody's optimality, how far into the future we need to look, right? So right now we are still in the phase of hypothesis. We actually can't see into the future, but let's presume that we have the ability to say far into the future. But what far into the future is it sufficient to recreate the Melody's optimality, right? So that's the question which they pose. So in this plot you can see on x-axis it's the view of the future in terms of cache capacity, and on y-axis we see it's the error rate compared to the infinite opt. So infinite opt means we can see the farthest future, right? So the y-axis, the less it is the better, right? So here if you see, based on this analysis, they found out that 8 times future access to a particular set is sufficient, 8 to 16 times to reduce the error, to 0 to 5%, right? After 16 times, it more or less, the plot kind of saturates. So if we have a good enough access of future, we 8 times access of future, we are in a good position to call the shots, right? So any questions till this point of time?
So this is more like what some prediction you're saying. Or how are you really like looking at 8 times in the future? Is it more like a prediction?
Yes, yeah. It's more like a prediction. We will go into that in detail. We will
Yeah.
see how to kind of recreate or reverse engineer those things, right?
Okay. Okay. Thanks.
Yeah, that we will dive into. But any questions till this point of time? Any other students? So that we can jump into the actual core of it. Let me quickly see the chat part if there is any. No. Okay. So I presume we are good till this point of view. So yeah, now the question just asked by one of your colleague, right? We don't have future information, but what we have is this. We have the past information with us, right? Now, if we kind of question or we kind of postulate a statement which is past a good predictor of future, right? So if we have good enough past information, so can we take a leap to future, right? So that's how this Hawkeye and Mockingjay and all the state of the art replacement policy question go ahead. So this is the bedrock key observation which they find. So what is it? If with the optimal solution, a load instruction has historically brought in lines that produces cache hits, right? Let me repeat it again so that we can get absolute clarity on this. If with OPT solution, which is the futuristic solution, theoretical solution, a load instruction has historically brought in lines that has produced cache hits, then in future there is a high chance that the same load instruction is likely going to bring in lines that may also produce cache hits, right? So it's more or less like depending on past. Obviously this is not the only observation, they will add much more sophisticated logic, but the crux is that in past, if certain load instructions, right, we have load and store in our CPU architecture, so certain load instructions which is a certain program counter has brought in some lines, if they have historically produced cache hits, there is a good enough chance that in future also the similar load instructions might bring up lines that can get cache hits. Now you may wonder, okay, you are just kind of saying, so let give us some real concrete example, right? So let's delve into a concrete example. Let's say this is how let's say a program is being executed. So we have the program counter values in this table, we have the instruction, and then we have, let's say, the memory block, right? Just for the simplicity. So now let's is there any similar can you kind of point me out, is there anything special in this particular table which you think you can point, or can we exploit this something somehow based on the PC value? Let me give a hint. So we have 4 PC values with us right now, right? So is there some similarity, some differences, something? So, right now what we have is this 4 PC values, right? Now, if you look at this first PC and the last PC, they are same, right? But one PC is bringing one block, that is block A, and other PC is bringing other block, which is block B, right? Now, let's say currently we are here, right? Let me give you a brief explanation of how the prediction works, right? So let's say we are currently here, and now this particular PC has block B, right? Now if we are in a position to predict whether the currently loaded memory block B, whether that will be a hit or miss in the cache, right? Do we have something to refer back in the history?
Yeah, at least from this set of instructions, we see that block B was not brought earlier, right? It was not brought into the.
That's a good observation, but that's can we build one more step backward? Let's say we don't have any reusability about block B, but do we have similar program counters here? So what we are trying to say here is, you look at the previous PC, right? So this is the
Right.
same instruction, right? So previously, when this particular instruction, this PC was executing, it brought in block A, right? So
Mhm.
this is previous in time, and currently we are here. So earlier it brought block A, and now it is trying to ask for block B, right? So we are currently at this point of time trying to take a guess for block B, right? So what we will do, we will look at, for the prediction of block B, we will look whether block A, which was brought in by the same PC, right, whether in past it encountered a hit or miss, right? So in past, if block A has encountered a miss, which was brought in by same PC, when this PC is bringing up this block, there is a high chance that this block may also encounter a cache miss. So this is a working example of this particular observation. Any doubts till this point of time?
Sorry, one question though. So these are all, we're only talking about demand, right? We're not talking about any prefetch here. All of this is all
Right,
only demand.
right. So right now, this is just about the demand blocks. We can integrate the prefetch stuff, but that's it's explained in much more detail in the paper. But right now, we are just talking about the demand.
Okay, okay, okay.
Yeah. Okay. So if we don't have any questions, so this particular working example, I think, is clear to all the students. So trying to build on this, we can see that there is a good amount of correlation, between the program counters which are bringing in the blocks, as opposed to the blocks themselves. So this is much more finer, right? So we are using PC as a metric to train, right? So now let's see. But still, right, even though with this, we still have to, even if we are storing 8 times the past history, right, we still have lot of timestamps or lot of access information to store. So if you look at a typical last level cache, let's say per slice, so we have typically 1024 sets, right? Now to store 8 times the history for each set, right, that will be too much of hardware overhead, right? So this is simply not feasible from hardcore implementation perspective. This is not feasible, right? So can we come up with any feasible solution? Can you give or think about some feasible solutions? Like right now we have narrowed down the problem, right? So earlier the problem was we don't have any indication of the future, right? So what we did, how far into the future we should look. So we restricted our access to the future to 8 times, but still there was a problem. We are not able to see future, but we can restrict our access to 8 times the past accesses, right? But now even storing 8 times the past accesses for an LLC, seems to be a too big a problem. So how can we reduce that? Any insights you people are able to think? Just a wild guess, maybe.
We can create samples of few parts.
Yes, yes, that's precisely the way with which this research begins. We need to go with the sample sets, right? We need to sample out few sets, right, which can be monitored instead of the entire 1,000 sets. Okay, so now, so there is a separate paper on set dueling and all, which kind of proves how just monitoring 32 sets out of 1024 sets still gives us, more closer or similar kind of performance. So we'll not go into the mathematics of it, but just for the sake of understanding, let's assume that these 32 sets are sufficient to, sample out the entire cache. Now we need to only store the history of, this particular 32 sets, right? Now, when we store the history of only these 32 sets, what we do is we are reducing the hardware overhead by a huge magnitude. So instead of 1,000, now it's just 32, right? So excellent point that we need to go for set sampling, right? Now we have 3 modules with us, right? So we have sorted out the entire future problem. We are kind of sorted out the history, which is the storage problem. So right now we have 8 times history with us, right? Now there are 2 parts which are left. One is decision making, and the third is the training. We have a lot of history. How do we train that history, and what kind of decisions we come up with, right? So for Hawkeye, these three structures are very important structures which kind of do all the metadata work in the background without coming into the critical path. Now we will understand how that works. So the sampled cache is the history part, the occupancy vector and OPT gen algorithm is used for decision making, and the PC based predictor uses for training, right? Now all these three steps which we are explaining for Hawkeye are more or less, similar to other replacement policies like Mockingjay, Glider, or any machine learning based replacement policy also. They may vary in the implementation details here or there, but the crux or the structure in which they are put in that place, remains the same, right? So let's now look at how an actual Hawkeye algorithm works when it's applied to a last level cache, right? So till this point of time, we are clear. Now we are only sampling, 32 sets for maintaining the history, right? So if there is any access, right? Now we are talking about last level cache access, right? There's a fine difference here. Now if there is any access to the sample sets, right? We are talking about this case, access to the sample sets, right? Now let's say this is the sample cache. The sample cache is used to store the history, right? The access history. Now we have timestamps per set, right? Now any one of you, can you take a wild guess why we require timestamps here for the sample sets? So timestamps here are access timestamps. So how can we use access timestamps? Is there any way? Maybe a wild guess. Timestamps are like access. So let's say block A is accessing, so the timestamp is 1. After that, block B will access, the timestamp is 2, right? So it's access, not actual hardware timing, but the access timestamps.
Can be like our RRPV value, right? Can be like our.
Not exactly the RRPV value, but yeah, on the similar lines, we can use somehow to make predictions. But we can put it in reuse values, right?
Okay.
More or less like a reuse values. But more important than that, these timestamps are helpful to look into the history and see what is the condition of the cache for that duration of time, right? Because we need substantive cache information in order to make future decisions. So we need the states of the cache, right? So let's say a 16-way cache will have 16 different blocks, all of them will be in different states, so we need to capture that event, right? So that's why it's important. So we have timestamps per set, so we'll discuss in detail. Now let's say there's an access to a particular block, let's say at access time t equal to 10. So this is a working example, right? So what we will do, the Hawkeye algorithm will go into the sampled cache, which is a history. So now history itself is stored in a separate set associative cache, right? So there is no data here, there is only the tag part and metadata, right? Here LLC, there is tag and data both, right? This history is only tag part. So at time t equal to 10, we see there is no history. We do a tag match, there is no history. So we put the block here, right? And maintain the timestamp, right? Now there is a next access, which is at time t equal to 25 at the actual cache, right? So we don't take any decision here right now. We again go to the history, but this time there will be a tag match because there will be tag also associated with here, right? Now when there is a tag match, we have these two timestamps, right? Now this is very crucial. Now I would request every one of you to please closely follow the flow of Hawkeye, but that's why here things get a little bit tricky. Now we have both the timestamps, which is 25 and 10, right? These two timestamps are now fed as an input to the occupancy vector, right? Which is the second structure of Hawkeye, which is used for decision making, right? Now we will go into detail of how occupancy vector works, but right now, just for the sake of understanding, assumes that it will give us a binary output, right? So once we have a tag match here, we have these two timestamps. These two timestamps are supplied to an occupancy vector, and based on this, the OPT-gen algorithm will be activated, and OPT-gen algorithm will say whether it should be cached or not cached, right? It will give a binary output. Now, based on that output, the program counter which brought this block will be trained. Now, whether if it says hit, the program counter will be trained positively, right? So it will be trained positively. If it says miss, the program counter will be trained negatively, right? Now, based on this PC, the actual cache, the re-reference prediction value, right, which one of your colleagues just pointed out, will be indirectly pointed out. So there will be a 3-bit RRPV value pointed out with the help of this prefetcher, right? So let me take slightly steps back to explain. So there's an access to the actual cache. We go back to the sample cache, we see whether it's a tag match, we give that as an input to occupancy vector. Occupancy vector will give us a binary prediction, how that we will see later. That prediction is being given to the predictor. That predictor is trained positively or negatively based on the binary output, and with the help of the counters we will put some thresholds and we will give an RRPV value to the actual cache, right? Which means on every access to a last level cache, we go in these structures in the background to assign an RRPV value here. Is it okay, confusing, or are you able to understand? If you can provide me some feedback.
This is for every access. Is it going to be the critical path?
Yeah, no. So it's a very good question here. So this will not come into the critical path because actually it was a cache miss, right?
Okay.
So whenever it's a miss, the data will actually come back from DRAM. So we have 200s of cycles with us, right?
Okay. It's only so update is happening only during the miss. Okay.
Yes. For hit also it occurs, but it does not go through all the structures. So that's a different way. We'll catch up on it in the later part.
Sure.
Yeah. Any other students? Any other comments or questions? Okay, I have not seen any questions on chat. So I presume that we are, good to go with this, right? So now we have kind of understood, how Hawkeye algorithm works, right? And how the RRPV bits are set. Now, this is the $1,000,000 question, which is how, because right now we are having the liberty to go to the sample cache, and right, we have the liberty to go to the sample cache, to the occupancy vector, to the predictor. Why? Because we are having history for the sample sets, right? We have all the metadata information for the sample sets. But let's say there is an access to the cache or to the non-sample sets, and if we took the ratio, the non-sample sets are like 97%, because out of 1024 only 32 are sampled, right? So what do you think should happen or is happening when we access the non-sample sets? Because right now we don't have any history, no data, no metadata, nothing. So how do we put an RRPV value here when we don't have this history? Is the question clear? Right? We don't have any history for the non-sample sets, right? That we all agree?
Agree.
Right. But we have to put a re-reference prediction value here, right? Now, how to do that? So, in order to do that, anyone suggesting something?
Do we have to we'll implement similarity checker?
Similarity checker in what sense, Lakshay?
Like accessing behavioral behavior of access.
You are close, but in what sense you are talking about?
Actually, I have made a guess. I'm not sure.
No, you're very close. You're trying to see some amount of similarity, right?
Neighborhood of the PC is that neighborhood of the PC?
Sorry.
Neighborhood of the PC, similar PC, right? Yeah, only a
Yeah.
small set of PCs. Yeah.
Yes. Thank you. So what happens is the PC predictor, right? That comes to our help. Now, why that comes to our help is that based on their observation on OPT, they found a strong bias for the particular program counter, which we saw in that particular example, right? Now, whenever there is an access to the non-sample set, they presume that because these 32 sets are sufficient to store history, So that kind of correlates that this 32 sets history is kind of good enough to train the predictor to this amount of time, that whenever there is an access to this non-sample set, we have the incoming PC, we take the incoming PC, we index into the predictor, we check the counters, and based on the counters, we will apply an RRPV bits to the non-sample sets, right? So this all depends on the bias or the confidence of the OPT algorithm on the PCs. So there might be some applications where the PC bias is 90%. So in that case, the RRPV which we put for the non-sample sets is pretty much accurate. But for another applications where the PC bias might not that be high, right? You can presume that the RRP value which we put here will not be able to mimic the OPT, right? It might still not be that bad value, but it will not be able to mimic the Bellidy's algorithm, right? So this is the crux for the non-sample sets. Now, for as far as Hawkeye is concerned, right, the prediction of Hawkeye for a cache hit or a cache miss, what it says that the cache averse line will be given RRPV of 7 and cache friendly line will be given an RRPV of 0, right? So some extra details which you can look into the paper. But now for that time, right, we just consider that this occupancy vector will give us a binary output, which is whether to cache or not to cache, right? So now we will look into detail how this OPT gen vector, right, the occupancy vector or OPT gen, which means trying to generate or reconstruct Bellidy's optimality, right? Now this is very important and I would be requiring your help because this is a step-by-step process. Now let's assume that the cache size is 2, right? So any moment we are above the cache size, there is no way even Bellidy's optimality, even the best algorithm will be able to cache, right? So now let's say this is the access pattern. So this is the future access pattern. We don't know this is the future access pattern. We are currently at time t equal to 0, right? So currently at access time t equal to 0, A is appearing. A was not there earlier. We are here. So we will set the occupancy vector value to 0, right? Now again we are here at time t equal to 1. B is coming for the first time. I request everyone to please keenly observe here. B is coming for the first time. There is no history of B. So we will give value B again 0. But at time t equal to 0, B is coming for the second time. And earlier it came at t equal to 1, right? So from t equal to 1 to t equal to 2, we will give the initial value of B to 0, but we will increment all the values to 1. So this 1 is still less than the cache capacity, right? So this means that this should be a hit, right? So the way in which you understand this particular working example is that we are standing at present, we are looking at past, and we are making judgments about future, right? So currently we are at time t equal to 3, which is C, which is appearing at first. We don't know whether this particular thing is appearing right now, right? So C appeared first, so the old values of occupancy vector will be forwarded. Now let's say D is again coming for the first time, similar values will be forwarded. E is coming for the first time, similar values will be forwarded. Now see, A is coming at time t equal to 6. Now A was there already in the past. So from this point to this point, all the occupancy vectors will be incremented by 1. So here you see 0 becomes 1, 1 becomes 2. Now it's still in the cache. So still we are within the cache size, right? Now F will come. Now can any one of you tell whether we will be able to cache D or not at time t equal to 8? Will the OPTGen algorithm be able to say that we should be caching D or not caching D? Because so what happens is because D appeared at 4, right? Every occupancy vector from 4 to 8 will be updated by 1. So still it is 2, right? So still able to cache, right? Now what will happen at time t equal to 9 when E will be appearing?
It will not able to.
Why it will not be able to?
Because from t is equal to what we say, from E to like D, it will become 3 cache, exceed the cache.
Right. So this particular value this particular value will be exceeding, right? So as correctly pointed out, so here when E will be appearing, this particular value of 2 will be coming 3, right? So now see, they are not knowing anything about future, right? We are not making any decisions by F and C. We are at 9, which is current time, and we are looking at past history and updating the occupancy vector, right? So in this way, at real time, in an online fashion, they are trying to recreate, right? So E will be a miss, right? So the OPT gen vector will say to the predictor, okay, when E is coming, you give it a bad value, because the initials, the past state of the cache says that even with the future knowledge, you will not be able to cache it, right? So it's better to detrain the predictor and put it and give E some bad RRPV value so that it will be evicted quickly from the cache. So the cache space may be utilized by some better applications, right?
So
So
sorry, repeat that again, please. I think this one we can follow. Okay. See the last part. Why is it? Why do we not like? Why do we give a bad RRP value? Say it again, please.
yes, so because the OPT gen algorithm, which is based on occupancy vector, which is
Hmm.
trying to reconstruct the Beladi's optimality, is suggesting that because the cache size is 2, right? And even with future knowledge, you will not be able to give that particular block a cache hit, because
I
the
see.
cache size is restricted, right? Now when we apply it to a traditional set associative cache, we are looking at one particular cache sets, right, which is 16 ways. So in a typical cache, when the cache set size is 16, if it increases 16 from here, so there is not even opt can give a cache hit.
Okay. Okay.
So it's better to give it a bad rrp value, it will be evicted quickly. Got it?
Okay, but when you look at it, right, in this case, in this example here, although we have only access pattern until like 11 instance of
Right,
time here,
right, yeah,
right? But
yeah. So, yeah.
going into the future, I think obviously uh, uh, we don't know. I think we, unless you have a little more longer sequence, we can probably not predict here. But yeah, given this is primarily because the size of the overall cache is not able to accommodate. That's what you're saying. I
Yeah,
understand.
that's true. And your point is actually also very valid. We don't know. This is still in the prediction realm, right? We don't
Mm-hmm.
know. This is what we are trying to predict by looking at the past information. We need to also correct ourselves, right? If the decision taking is going in the wrong place, we need to give a negative feedback also, right?
That's correct. Yeah, yeah.
Yeah, that's purely correct. So that's how we need to adjust. Otherwise, just purely relying on past to take future decisions might cost us, huge in terms of performance, because not every time the past will be able to, kind of reflect the future, right?
Okay.
So that's perfectly valid thing. And because we have a limitation on the working set example, we are restricting ourselves to 11, but that may go anyway, right? Okay, yeah, so lot of good points are coming out of discussion. So okay, so any input on C then? What will happen when C will arrive at time t equal to 11? C has appeared in past at time t equal to 3. Will we be able to cache it? What the OPTGen algorithm will suggest?
On the same lines as C probably will not be able to catch C also.
Yes,
I'm sorry.
yes, yes, that's correct. Now, because already we have lots of 2, because we have already exceeded the cache size, right? Now we will not be able
Yeah.
to cache. Yeah.
Okay. Okay.
Basically, they translate the caching problem into the overlapping sub problem, right? So that's a separate mathematical problem. They try to translate this problem into that problem and try to solve it in that way, right? So this is occupancy vector reconstruction for you, right? Now to quickly summarize Hawkeye, right? This is the kind of hardware budget which we are looking at, right? So if we together club all the budget, which is the extra hardware or supporting structures used other than our last level cache, it comes up to a 28 kb. So that's why this research paper was, accepted in this ISCA conference, and it also appeared in, it also came first in the cache replacement championship, which appeared in 2015, because it uses, I think the hardware budget allocated to them was something less than 32 kb, and they did it in 28 kb. So they were top performance in below 32 kb budget, right? Now, if you closely see the hardware budget, we see sampler takes 12 kb and replacement state per bit takes 12 kb, right? The predictor and occupancy vector kind of, takes 4 kb. So storing history, and that too using the sample sets. Now imagine if we are not having the sample sets, this might have shooten up like anything, right? Yes. Now moving to Mockingjay paper. So it's actually a very small. It's like, a big brother of Hawkeye. So the core concepts of Hawkeye will remain same. Even the author Akanksha Jain is similar in both the papers, right? So this also appeared in one of the prestigious conferences, which is the High Performance Computer Architecture in 2022. So if you look at real times hardware cost efficient replacement policies, this Mockingjay is the current state of the art. So this is the current state of the art replacement policy, and the official name is effective mimicry of Belledy's min policy, right? So at a high level, as opposed to Hawkeye, cache replacement here at Mockingjay is a multi-class problem rather than a binary classification, right? So rather than classifying line as a cache friendly or a cache averse, Mockingjay classifies it, in a various spectrums. So the goal is to determine the estimated time of arrival for the incoming line. This is the catch, which means if currently I'm indexing the last level cache, can I predict a access time? That is, it will be coming after 25 accesses. It will be coming after 30 accesses. If we are able to predict at that level of granularity, the amount of prediction or the accuracy of the prediction is much more, finer in this case. And it also allows for, fine grained ordering, and because it goes for this fine grained ordering, it is, much more robust to prediction errors, right? As just pointed out by one of your colleague, that there is still a chance for prediction errors. So you should design a replacement policy which is much more resilient to the prediction errors, right? Now the structures in Mockingjay remain similar, just we don't have the occupancy vector. We directly train it on the reuse distance predictor. Now, how do we do that? So let's say the first three steps are similar. Time t equal to 10 something accessed. We have the history. Now there's a second access at time t equal to 25, right? So we'll go into the sampled cache. We have these two values. But now instead of going to the occupancy vector, we will directly train the predictor. Now you may ask, how can we directly train the predictor, right? This directly training is possible if we have this program counter here, which we already have. So they will directly train the predictor, but the main important thing which is differentiator here is instead of a 3-bit RRPV value, they give us 7-bit ETA values directly on the counter. So now we have a bigger spectrum. So 7 bits is 0 to 128. So and they actually assign ETA values here. So they have 28, 78, 66. So what happens is the ordering error becomes less, right? So this is the only difference between Hawkeye and Mockingjay. There are some fine differences, but that's just the implementation detail. But at a high level, that's how simply they vary with each other. The fundamental difference is at the time of applying the ETA values, right? Now, what might be the advantages of Mockingjay over Hawkeye? We will quickly skim through it. It is more resilient to prediction inaccuracies, right? Why it is more resilient to prediction inaccuracies? Because in Hawkeye you will put simply RRPV of 0 or 7. So if let's say that RRPV of 0 you put it in wrong manner, right? Because of the prediction inaccuracies. So all the subsequent blocks, right, which are appearing after this for the same PC, because it is now trained on PC. So if one PC is giving 0 value, other blocks from the similar PC will also give 0 values everywhere in the cache, right? So that will lead to cascading effects. But in case of Mockingjay, that is not the case because the ETA values are there. A small difference in ETA values might not be that big, and they actually prove it experimentally. Details are in the paper. The impact of classification error is localized, and they interpret priorities lately, which means that when they want to take this ETA value, they will actually assign it with the help of when they are putting it, and it will not remain static. So these timestamps are evicted on every cache access also. So on every cache access, they will go to all these structures, and if there is a hit, they will also increment here. So the ETA values are kind of incremented at much more finer scale, right? So these three are their advantages. quickly going through the experimental setup. So for those who want to try this, at the hands-on level, we have both of them implemented in the ChamSim simulator, which is, pretty much open source, and you can quickly set it up and try get it running. This is the cache configuration which they used. Now, looking at performance, just looking at the single core performance, on y-axis we have speed up percentage improvement over LRU. On x-axis we have spec benchmarks and graph benchmarks, right? And for comparison, we have Ship, Hawkeye, and Mockingjay. So Ship is another version which we will discuss some other fine day. So if you see at GeoMean, if you see, Hawkeye shows a performance improvement of 4.5% over LRU, and Mockingjay shows a performance improvement of 5.7% over LRU, right, for the single core application. Now you may wonder that, oh, we have spent 50 to 60 years after Bellidy's optimality, right? It appeared in 1966. So from and LRU appeared somewhere, 1970, 1980. So from 30 to 35 years, we still are able to improve only 4.5% performance, and Mockingjay is able to improve, 5.7. So it's really difficult at the microarchitecture level to get performance improvement. You might see in some other workloads the performance improvement might be 20%, 40%. That's fine. But at a high level, averaging across all, the improvements are very less. That's why microarchitecture is all about trade-offs. You need to find perfect trade-off between performance and hardware overhead. Now, for LRU evictions, the crucial point which one of your colleague pointed out, I think this is where Mockingjay actually wins over Hawkeye, which is sometimes when the accuracy of the predictor is bad, what happens is both Hawkeye and Mockingjay fall back to the LRU evictions. They say that, okay, no more relying on predictor because the predictor is just going haywire. So what they do, they fall back on LRU evictions. So you see, the Mockingjay's ability to fall back at LRU evictions is less, which means Mockingjay takes more decision based on predictor, and Hawkeye falls back at LRU nearly, some 10 to 15%, but Mockingjay fall backs at LRU some 7 to 8%, right? Which means the resilience at Mockingjay is much more higher as compared to Hawkeye, right? So we'll quickly discuss some key takeaways. So both Hawkeye and Mockingjay are kind of trying to mimic the Bellidy's optimality policy, right? And the accuracy of the predictor is roughly near 90%. Now, which can further be pushed. If we really want to push, this to the wall, we can still deploy some machine learning based techniques, with some low overhead to push this 90% to, let's say, 95, 97 or something like that, right? So that's one way to further build on top of this. And the other way is, again, I think one of your colleague pointed out this during our discussion, is do we consider prefetcher and multi-core impact, right? So both Hawkeye and Mockingjay are integrating themselves with prefetcher and also for multi-core. So the details are in the paper. So I have purposefully not included it so that the talk will lose from the main point, which is the actual working. But there are still few points which you can leverage by integrating this, supporting structures or going in multi-core. How do you handle the interference, right? So that can again be enhanced. So that's the points, and yeah, that's pretty much from my side. Thank you very much. I would be really happy to take any questions or discussion points. Thank you.
One question. No, thank you so much. Very, very, very insightful. Very, very nice. Thank you, sir. Only one thing I had question for you. The last, I think you mentioned that you're not going through the prediction vector, right? Sorry, in the case of Mockingjay, you directly go increment the counters, right? So you
Yes.
for every access, you said you're incrementing, right? Isn't that in the critical path then? For every access, we're going to go increment the counters.
See, that's a very good question. What happens actually is they kind of use some fast forwarding technique like some quantums, right? So let me quickly pull out that slide number where it mentions the hardware. Yeah, yeah. So is it visible, right?
Yeah,
Yeah. So if you look at the occupancy vector, right? So if you look,
yeah,
the quantum is 4 accesses here, right? Something is mentioned here.
Yeah, yeah.
So this four axes is actually trying to speed up the critical path. So your question is actually bang on when you are in the when on every axis, whether it's a hit or a miss, right? And specifically on a cache hit, if you are going through that critical accesses, right? They
Yeah.
actually fall into the critical path. But what happens is we also have a data part in the cache, right?
Mhm, mhm.
We what happens is when there is a tag hit, we take the tag, we go to the data part, and we supply it to the upper levels of cache, right?
Right, right, right. Yeah.
So somewhat accesses happened, but they have not mentioned, clearly in the paper.
Okay, okay, okay.
Yeah, but in the implementation, if you're asking from the implementation point of view, it will not appear on the critical path. That's their call. And somehow the microarchitectural features are adjusted in such a way that it will not fall in this path. That's what the conventional wisdom
The
says.
claim is okay. Okay, okay. Yeah.
Yeah,
Thank you so much. Thank you.
yeah, yeah. Thank you. Any more questions?
Sir, can you explain that part ki how program counter predictor is working for other sets that
Okay, got
that
it.
are
Yeah,
not including? Yeah, sir.
sure, sure, sure. I will pull back. You are saying about when there is an access to non-sample sets, right?
Sir, yes.
Sure. Yeah. So see, what happens is because we don't have any access for these sample sets, right, Muskan? We don't have any history for this, right? So
Sir.
still we have to take a decision. But now when there is an access to non-sample sets, we are actually in a fix, right? We don't have any data, but because there exists a bias within the program counter itself, right, which we discussed in the motivational slides. Let me pull it up quickly for you. If you look at the program counters, yes, yes. So this is the slide which I wanted to point out. So right, we kind of discussed or gone through this small example, right, where we see that the program counters, the PC is bringing in different blocks, right? Now let's assume we are currently in this particular PC, right? And let's say this block B is now mapping to the non-sample sets, right? Is it clear? But now, when this same PC has accessed block A, now let's assume that this block A was accessed in the sample set region, right? So this block A has trained this particular PC in one manner or another, right? But we don't have any access for block B. But what we have is the same PC bringing both the blocks. So if block A was accessed in sample set, it has trained the PC. So when block B is accessing, it was brought in by the same PC, but it is in non-sample set. But we can use this, right?
Yes, sir. What is PC here, sir?
PC is the program counter,
The
which is the
program
instruction
counter.
pointer, yeah, which points to the
Sure. Yes.
instruction currently being executed.
Understood, sir.
Got it? Yeah. Okay. Any more questions or any points which you like to discuss?
So we are running this problem, Hawkeye problem, in on 4 core or single core.
So the current results which I showed are for single core, but the authors have detailed their analysis for 4 core, 2 core, 8 core, everything is there. They have their own challenges. They scale up certain values. Your question is absolutely correct. It will not be a simple transition from single core to multi-core. There are some scaling factors involved, but that is applied to the sample sets and the predictor, right? And that's how they scale it for multi-core. But they have the results for multi-core.
Okay.
So one couple of more questions, sir. One is obviously the goal is obviously to ensure that we continue to improve on performance. Of course, the sir and Sri Shindu sir has been teaching us recently on the Mirage and Maya cache and so on as a
Right,
part of security aspects of it. And the
right,
goal is obviously is to the best is to really get as close to as a set like a fully associative cache, right? Because set associatives, which is causing our the problem of all this security aspects and so on. But given this emphasis is primarily on performance, do you think that we still this will obviously still there could be a potential of security issues on this where somebody like an adversary can really cause do the like a either like a flush and reload all those kind of things are still problem with this, right?
Yeah. That's exactly correct, and you have pointed out the flaws. Actually, they all
Yeah.
are still vulnerable to all the state-of-the-art conflict-based attacks, or this evict reload, flush reload, and all these attacks. Right? They are still
Right.
vulnerable.
Yeah.
Now there is still a lot of room for combining these two seemingly vertically opposite, or let's say 180-degree different problems, right? If you are going for
Right. Yeah.
performance, there is a high chance that you will fall into this trap of attacks. And if you are solely trying to stop these attacks, you might lag hugely on the performance side. So that's the trade-off with which we have to play. And now you need to fundamentally rethink how to design systems, right? That much is, I think, pretty much sure. But that fundamental rethinking should also not be something that will cost too much of hardware budget or something, right? The critical
That's
path
yeah.
should
That's
still remain the same. So
right.
yeah, it's
I
a
think
hard.
as you rightly said, sir, two things. One is obviously to make sure that somehow, as this entire space continues to evolve, we have to. I think this will be really good to see where we can blend some kind of trade-off, blend of both the performance and the security aspects. I think that's what I
Yeah,
see.
yeah. That's always there, and it's pretty difficult. But if you have a good understanding of how the microarchitecture components kind of interact with each other, right?
Mhm.
There is still a way. We are working on it, but we need to think about it in a bit of a different fashion, right?
Right. Yeah.
Trying to balance the trade-off might become very tricky sometimes. It's like sometimes it's very diametrically opposite, right? So
Yeah.
if you go to increase some particular metric, the other metric kind of falls down. But yeah, that's how we are computer architects, right? We deal with trade-offs.
Right. Yeah. No, thank you
So
so much. Very insightful. Very wonderfully presented. Thank you so much, sir.
yeah. Thank you all for listening. Any more
By the way,
questions for
sorry,
now?
this is being recorded. I think in case we want to later on use the recording, somebody I forgot to ask. We should have recorded this, right? Did we?
Uh, Guru, are we good with recording? Are we still going?
Yes, sir. The session is being recorded.
Yeah.
Oh,
Very
thanks.
good.
Yeah.
Thanks, Guru. I just want to confirm the recording it later on. If you want to use it for our, go back and look at the video one more time and probably we want. Yeah.
Sure. Yeah. So that's good thing we have recorded, so we can have the. Okay. Any more questions, or are we good to call it off for today?
Very good. Yeah. Thank you so much.
Yeah. Thanks. Guru, I think uh, we should call it off,
Yes, sir.
right?
Yeah.
Yeah.
Yeah. Thank you very much, sir.
Yeah. Thank you. Thanks, Guru, and thanks to all the participants for